All right, this is Math 146, Section 7.2, Video number 2. We're continuing the idea with the geometric sequences in series, and we developed the idea of how to find the sum of a geometric sequence up to a certain n terms. So if we had a finite number of terms, we developed how to figure out what that sum is. And we're actually going to still take that very sum to develop how you would actually find the sum of an infinite geometric series, meaning that the terms don't ever stop. And that's kind of what the actual definition of a series is. Sometimes we just call them series, but they're typically known as infinite series. And here's the concept. Because a lot of times people ask, well, how can you take an infinite number of numbers and add them up and actually have a sum? How does that possibly work? Well, it does work for certain circumstances. If we were to take, and we've already done this one, if we were to take the sequence 1, 2, 4, 8, 16, and so on, and say, can we add up all of the terms of that and actually approach some kind of an actual number? And the answer to that would be no, because you're just making the numbers bigger and bigger and bigger. So you're going to constantly be adding bigger and bigger numbers together. Well, that's just going to completely go off towards infinity. In other words, the numbers are just going to get so big, but they're never going to have a bound. They're never going to stop. So you really can't add them up and get a finite number out of it, get a sum. And for those people asking, well, why can't you just say it adds up to infinity? Well, infinity technically is not a number. It's a concept. It's a way for us to describe things which go on forever. So it's really not a number. You will hear that probably more than likely several times again when you start getting into the higher level math, specifically Calc 2 will deal with that. Or I'm sorry, Calc 1 and Calc 2, when you start talking about limits. But we can take something like 1/2, 1/4, 1/8, 1/16, and so on. That one is also a geometric. In this case, the R value would be 1/2. Up on the top one, it was 2. The R value would be 1/2. That one actually does have a sum. It has a way for us to add it up. And again, this is very conceptual, but a lot of people start asking, well, how is this possible? So the easiest way that I like to show is I like to create a box. And I definitely show this for all of my calculus classes as well. But the idea is if I were to take that box, which we know to have some kind of a finite area, because if I say that the top has a length of 1 and the side has a length of 1, we know it's now a square. And we know that that has to add up to an area of 1. Well, what if you were to take that box and you were to split it in half? Well, now this side has an area of 1/2. What if I were to take the other side and split it into a half? Well, now basically each one of those boxes is a fourth. And then if I were to take that bottom fourth and split it in half, that's an eighth. If I were to take that remaining piece and split it in half, now I've got a 16th here. And I could keep doing that infinitely, splitting these boxes in half infinitely. It's going to get really, really small, but I technically can keep cutting each one of those remaining boxes in half or multiplying them by a half. But yet, we know that the sum of all of that area has to add up to 1 because it is a finite area. So there is a way for us to take an infinite number of things, add them up, and get a finite number. And there is a sum, there's a formula for this that we are going to develop. And again, this is going to be a little conceptual, so you have to kind of take this for what it is. And this is, again, something that will be covered much more when you get to calculus. But we know already, and I am going to factor out that a sub 1, that this was our sum. Oops, I don't know why I wrote that 1 there. Of a finite number of terms. So that would be our sum of n terms. Well, what I can do is I can basically redistribute the a sub 1. I don't know why I pulled it off to the front there for this. So I just redistributed the a sub 1 to the top. And what I can do is I can take that and I can split the numerator over the denominator. So I can take the a sub 1, split that over 1 minus r, minus, and then I can take the a sub 1 r to the n and split that over 1 minus r. And again, the idea is if I have a certain type of r value, that as I let as I let n get really, 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 really big, the values that you get from the r to the n are going to start to approach 0. And what do we mean by that? Look at this example here. As the numbers keep going further and further out, you're going to get 1 over 32, 1 over 64, 1 over 128. The further and further you go out, those values are going to get so incredibly small. You're going to get like 1 over 15 billion something trillion. I don't know what. They're going to get really, really small. 1 over some massively large number that basically it becomes 0. So if you were to look at this right side here, this piece right there, if I were to let this r value be some value that basically lies in between 0 and 1, not including 1, this whole numerator is going to start to approach 0 because this part is going to get really, really small. And if that starts to approach 0, a sub 1 times 0 is still 0, and having 0 on the top of a fraction is still going to be 0. So ultimately, as those n values get really, 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 really big, that whole right side is going to go to 0, which leaves us with the sum being a sub 1 over 1 minus r. Now again, here's the key. The absolute value of the r values, because it doesn't really matter if it's positive or negative, the absolute value of the r values must be less than 1. If it is 1 or it's bigger than 1, then again, the numbers that we have that we're going to start adding are just going to keep getting bigger and bigger and bigger. If this happens, and again, this is a concept that's going to come to play much, much more in higher level calculus stuff, but if you have a sum which just doesn't approach a number, just keeps getting bigger and bigger in either direction, it's what's called divergent. Okay, I'm not really going to write that down per se, but if the numbers don't approach some kind of a finite value, it's just divergent if it goes off towards infinity. If it does approach a sum, in other words, if you can plug your stuff in and get an actual sum here, and because the absolute value of r is less than 1, it's called convergent. It's going to converge to a specific number. Again, that's a concept more for calculus. I'm going to leave that to the calculus teachers to really ingrain that one in you. But just know that you can find an infinite sum of terms as long as the absolute value of r is less than 1. And the formula is s equals a sub 1 over 1 minus r. So now let's go ahead and take a look at an example and just show how easy it actually is. Oops, it's supposed to be an e, to find that sum. So we're going to have the sum as k goes from 1 to infinity. So now it's not to the n, it's to the infinite number of terms of 2 times 2/3 to the k minus 1 power. So what you need to basically be able to do is you need to say, first of all, what is r? Well, r is the thing which is being raised to that k power. That's the 2/3. So then can I find, excuse me, is the absolute value of r less than 1? Well, 2/3 certainly is less than 1. So you would simply look at it and say, well, r here is 2/3. The absolute value of 2/3 is definitely less than 1. So we know that this is going to have a sum. And if that's the case, what I need is the a sub 1 value. Well, the a sub 1 value is the first term. So if you simply start by plugging 1 into the k value here, you get 1 minus 1 as a power, which is 0. 2/3 to the 0 is 1, but don't forget you're multiplying it by that 2 out front there. So the very first term, a sub 1, is 2. So then according to our formula, it's 2 over 1 minus the r value, which is 2/3. So we get 2 divided by 1/3. Dividing by a fraction is multiplying by its reciprocal, so we get 2 times 3, which is 6. So the sum of this particular series, and it's an infinite series, adds up to 6. Okay, really not a difficult process to do. I want to do one that I think is far more interesting. It's a concept that a lot of people have a hard time with. They really struggle with this one. Most people, if you say, I'm going to give you the decimal, the repeating decimal, 0.99999, and so on. So we take the repeating decimal, 0.99, put the little bar over the top just indicating the nines go on forever, or you could write the ... afterwards. Believe it or not, that equals 1. And again, a lot of people are going to say, well, wait a minute, it's 0.999. It's actually not 1. It's going to be really close to it maybe, but it's not 1. By a mathematical definition, this is 1. And this is why this works. If you were to take the decimal, and we're just going to use the first 3 parts here, 0.99, just to show how this works. Sorry, 0.999. That is the same thing as 0.9 plus 0.09 plus 0.009. Okay, if you add all those things up, you would get 0.999. Sorry, left off a 9 again. Now let's say that I want to take that same thing, but make the numbers go on forever. Well, the same first 3 terms haven't changed. But that's going to keep on going. And ultimately, what you're going to find here is that that is the same thing as 9/10 plus 9/100 plus 9/1000 plus and so on. This is going to be a geometric sequence of terms. And when you add them up, it becomes a geometric series. And the reason is because what am I multiplying by every term to get to the next one? It appears that I'm multiplying by 1/10. And if you weren't sure, you take any 2 consecutive terms, divide them, and you would get 1/10. So in this case, r is 1/10. Okay, because r is 1/10, we know that if we add up the infinite number of terms, it's going to add up to a finite number. A sub 1, in this case, is 9/10. So, according to our formula, if I want to take the sum, as k goes from 1 to infinity, of 9/10 times 1/10 to the k minus 1 power, we know that is a sub 1, 9/10, divided by 1 minus r, 1/10, and you get 9/10 divided by 9/10, which indeed is 1. So again, it's not exactly something that's intuitive to a lot of people, but it does show that the infinite number of 0.999s, in other words, 0.99 repeating forever, is actually 1. Okay, the sum of all those different terms have to add up to 1. All right, there are plenty of good applications for these geometric series, specifically dealing with finances, annuities, exponential growth and decay models, all kinds of stuff for that, which are great applications. But I think as far as the math is concerned, that's pretty much all we need. So we're going to go ahead and end the video there. We've got one more section to cover, 7.3, which is the binomial theorem.